5.1, the reduced mass problem, and that was 5 points out of 5 to go through that. All right, then I clumped together the next bunch, 5.2, 5.3, 5.5, and 5.7, all together. All right, and what all those problems had to do with is, once we got the idea of reduced mass, it was playing around with the reduced mass to see how the different energy spectra changed by using the correction of the reduced mass instead of the regular mass, okay? Now, I posted the solutions to those, all right? And they're tricky and they're clever, all right? And so I don't expect that anybody should be able to do them, all of them right away. You should be able to get somewhere.
Some of these problems you can't do without an equation that he doesn't give you in the book.
There's no question. It's very challenging, all right? And so go through those and do the best you can. If you get stuck, it's more about the idea. And we really use the idea about the reduced mass. That's the thing that I'm trying to pull out of that. Okay, so for those 1, 2, 3, 4, 5 problems, those are worth 10 points. Okay, the next set of problems I was looking at are 512, 513, and 514. That was another set, and those are worth 10 points. And those are some of the problems I'm going to go over today.
12 to
Okay, just hold on to them if you would, please. What's that?
12 to
Okay, and then that was 512, 13, and 514. Okay. Then the next set of problems was 515 and 516. And that was 10 points. And then on the 516, I also wanted you to try plotting the distributions of the Fermi-Dirac distributions, the Bose-Einstein distribution, and the Maxwell-Boltzmann distribution. So that was in that set with 515 and 516. And then finally, today's 518 and 519. So what I truly expected by today that you should probably have in 512, 513, and 514.
Well, I thought you wanted all of
Should
them.
I put it in?
You can put them all together if you want, but where I expect you to be at in your work, right? So I'm not going to hold you to specific deadlines, but where I expect you to be at your work is through those types of problems. And then after today, you should be able to, well, even after last week, you should have been able to do 515 and 516. And then after today, you should be able to do 518 and 519. Okay? Okay. So, let me talk about some of the ones that I think you should have done for today. All right? And those include the one when we start to talk about what we did last class is we looked at fermions, and we looked at the total wave function. And for fermions, we determined that the total wave function had to be antisymmetric. And so what we then did is we considered 2 electron cases, and we made 2 electron total wave functions. And those 2 electron total wave functions consisted of a spatial wave function and then a spin wave function. What we found for the spin wave functions is it came into 2. It came into a triplet and a singlet. The triplet was symmetric, the singlet was antisymmetric. And so then we had to combine those correct symmetries with the corresponding spatial part of the wave functions to get a total antisymmetric wave function. All right? So that's what these problems have to do with. The biggest result out of all that is that what state of 2 electrons is the lowest energy?
Symmetric.
Okay, so it's the symmetric state of what? The electrons, right? The electron
Space.
spin.
Spin.
Is it? You tell me. So where?
Space. We did
So we've got 3 things here. We've got the total wave function that has to be antisymmetric, and it's built out of a symmetric or an antisymmetric space and a symmetric and antisymmetric spin. So you guys tell me, what is the answer?
For the ground state.
The lowest energy of 2 electrons is what?
So you have to have them closer. Closer together, right? It was closer.
asymmetric space and symmetric spin, because you needed this triplet has the symmetry, but you need the asymmetry of the space to get them closer together.
Okay, I agree, I don't like what you said 100%. I agree with some of it. What you said is the triplet spin is symmetric, and therefore the triplet spin would go with the anti-symmetric space.
Right.
Now, I agree with you, that is the lowest energy. Okay, why?
Because antisymmetric space configuration would put the electrons spatially closer together.
The
Less
anti-
distance,
I can't remember.
and the spin would determine the location. in-
Okay, so here's a very important thing that I asked you guys to look at. We calculated the expectation value of the distance between two particles, x1 minus x2, right? And then we considered the implications of that expectation value for just distinguishable particles, which would be Maxwell-Boltzmann type distribution, and then fermions and bosons, right? And what we found out is, well, I said fermions and bosons
No,
again.
psi plus and psi minus.
Let's say the symmetric and the anti-symmetric spin. What did we find? We found that the expectation value for the,
Symmetric spin was, they had, because it was symmetric, they were actually further, as there's the distance,
Yeah, the distance is 1 over the distance.
okay,
So
so
you
let's
wanna go-
everybody,
You want
So-
a large distance to get a small value.
okay. The scoop is, yeah, let's go down and get an example. All right, we're talking about the result on page 208. And what it says is the symmetric spatial wave function lets the two particles get closer. And the anti-symmetric spatial wave function keeps them further apart.
It's like a push force.
Okay, now, which one do you want to give you the lowest energy?
then be further apart.
You want the one that are the furthest apart, because the wave function that lets them get closest together, right? If they're electrons, they have an electron-electron interaction and an electron-electron potential, which is positive, so that increases the energy. So you want the electrons to be as far away as possible, which means the anti-symmetric space. But now to get the total anti-symmetric wave function, you've got to go the anti-symmetric space times the
Symmetric space.
symmetric spin, and the symmetric spin is the triplet. So that's the big result there. Okay? It's a tough story. It's not at all trivial to get that story right. All right, and that forms the essence of Hund's rule, and I'll talk a little bit about Hund's rule and some of the problems today. But before I go much further, in one of the homework problems, I believe it was 5.7, right? In homework problem 5.7, you have a really neat trick. And that really neat trick is a method to figure out a total antisymmetric wave function. All right? And so the way you do it is construct a determinant.
I didn't do it that way though. I did it with epsilon ijk.
Okay, you can do it a whole bunch of different ways. All right? And it's easy to make an antisymmetric wave function with two particles. It's psi A, psi B, minus psi B, psi A. But then when you start to get more particles, like say you get 3, it's not at all clear.
No, because then depending on, you have to reverse the orders and.
Right, so what you can do is form essentially the determinant of a matrix with your wave functions, and that determinant of the matrix will be antisymmetric. And so it's called a Slater determinant.
I thought it was faster in these permutations because you could see it much quicker.
Yep, you can do it that way. All right? But I just wanted to mention that.
Write out the full determinant.
Yeah. Okay, everybody okay? So how do you calculate a determinant? Well, you go like Psi A, Psi B, Psi C, Psi A, Psi B, Psi C, Psi A, Psi B, Psi C, right? And then you calculate the determinant of that. Okay, so, you know, for example,
You can label it to make it
yeah, well, it was Psi A, Psi B, Psi C, and Psi A, Psi B, Psi C, and Psi A, Psi B, Psi C. And I think you'd have to go like of R1, 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 and R2,
Right.
and R2, and R2, and R3, R3, and then R3. Right? So if I told you to find the total antisymmetric wave function, one way to do it is kind of the classic way you do it, calculating a determinant. So I kind of go across the top row, and I would go psi A of R1 times the determinant of these things. So psi B of R2 minus psi C of R3. All right, and then what do I do?
Minus psi B of R1.
Okay, so you guys get it? And then finally, is plus psi C of whatever. All right, and that's called a Slater determinant. Okay, let me move on to some of the homework problems, all right? Some of the other homework problems. All right, and specifically what I'll do is I'll jump to problem number 513 on Hund's rule. All right, and I'll just give you a quick take on that. Again, the most important Hund's rule I want you to remember is that first one. That the state of lowest energy is going to be the state of the highest spin, right? Because the state of the highest spin will have a, what type of wave function? Symmetric or antisymmetric?
The highest spin is a symmetric wave function, but
Therefore, the space
is
of-
asymmetric.
The antisymmetric, which will keep the electrons as far apart as possible. Okay?
I didn't
So-
even try VNC.
I'll show you how it works.
Figure out what you're talking
All right, so the first one is, the Hund's rule, the first one said, all things being equal, the state with the highest total spin will have the lowest energy. That's what we just said, because the state with the highest total spin must have the symmetric wave function. So the symmetric spin wave function, and therefore antisymmetric space. What would this predict in the case of excited states of helium? So we did that problem, right? Helium, you can make singlets and triplets of the excited states. So what's the answer?
Triplets in
The
that.
triplets in helium are going to be lower energy than the singlets in helium. And you call the triplet states of helium the orthohelium.
Yeah.
All right? And the ortho goes with the antisymmetric space.
Because the antisymmetric spaces are far enough from each other.
Right. And then the perihelium is the lower energy, is the higher energy, because the perihelium is the symmetric spatial, which gives you the singlet spin. Okay? All right, so we've got that. The next question, and I'll just sketch it out. And guys, I'm not going to say test you on these Hund's rules. All right? I just want to give you a flavor for how all this works, because I didn't even explain all the other ones, but you'll be able to see it in a little bit. Okay. So let's take a look at carbon. All right, so first of all, a good procedure for figuring this out is just start off with carbon. So carbon is a group what? 4? So it's a 1s squared, 2s squared, 2p squared. Yeah?
Yeah.
Okay, everybody should know carbon. Hydrogen, everybody should be able to get through the first 2 rows. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, neon.
No, you skip one.
Did I screw up?
Fluorine.
9 is fluorine.
Fluorine, neon, okay? So everybody should know that. And below fluorine is like chlorine or something like that. And below neon is argon. And then over here it's hydrogen, lithium, and then rubidium's down there and everything.
Rubidium is like the number 37.
Okay.
This
So it'll be a group
potassium
1.
between
It'll be a group 1.
the- Sodium potassium are between lithium and.
Okay. So let's take a look at this. So these are closed shells, right? And so the 2p has a px, a py, and a pz, right? You know, if I were to write it, it'd be like a 1 minus 1, a 1, 0, and then a 1, 1, right? These are the projections. So these have different quantum numbers. Okay, so what's going to happen here? What's the lowest energy for the spins? How are the spins going to line up in here?
They'll fill one each.
Okay, they would fill up one each. They would do something like this, right? They wouldn't do this, and up and a down. That's Hund's first rule.
You have to fill out the rules.
Okay, it's going to fill up the maximum. So here we go. All right, so that means S total equals what? So Hund's number 1 is that S total equals 1. Okay? So let's look at Hund's rule number 2. And Hund's rule number 2 says, consider now the total angular momentum. So what can L total be? I have 2 p orbitals, so what can I have for L total? I can have 2, 1, or 0. So remember, L1 equals 1, L2 equals 1, because I have 2 p electrons. So the L total can go from 1 plus 1 all the way down to 1 minus 1.
Right.
So L total can be 2, 1, or 0. Okay? So here's the scoop, all right? Hund's rule set number 2 says that in general,
Consistent with rule number 1,
so the rule number 2 is L total should be max. So you want the max X, S, and the max L, all right? But here's the scoop. For this particular case, if I have S total equals 1, what type of spin wave function do I have? Symmetric or antisymmetric?
symmetric.
It's going to be symmetric, all right? Now, let's look at L total. So I'm tempted to write down a 2. Right? Tempted to write down 2, but for 2, I would have to have 2 p orbitals, and p orbitals are antisymmetric. All right, so the way it goes is that s orbitals are symmetric, p's are antisymmetric, d's are symmetric from chemistry, s, p, d, f. S's are symmetric, p's are antisymmetric, d's are symmetric, f's are antisymmetric.
G, H, I.
Okay? So if I have 2 p orbitals and they're both antisymmetric, and I multiply those together, it would be symmetric.
Right.
And then it would be a symmetric times a symmetric,
That can't be happening.
which would give me a total wave function that's symmetric. So can you have that? No. All right? And so if you can't have that one, what's the next highest one?
1.
A 1. So Hund's rule number 2 says that, look, we're going to have an L total equals 1. All right? So if I have an L total equals 1, I have a P state, the total L of a P, right? If I have L total equals 1. And if I have spin total equals 1,
Symmetric because symmetric.
well, what do I have here? A singlet, a doublet, or a triplet?
It could be a singlet.
No, it's a triplet. Remember, it's
Like
2s plus 1. So I would have a triplet P.
J would be 2.
All right, and if I have a S total is 1 and the P total is 1, then J can be 2, 1, or 0. So I could have a 2, 1, or 0.
Or that's the absolute value.
So if this were an atomic physics course, guys, I would kill you on this stuff. You know, on a test, I would require it. But we're not doing the atomic physics. This is a flare of the atomic physics, not a full course on just atomic physics. Okay, so I'm not going to kill you on this stuff, guys.
Can I ask a quick question about that? Is Herzberg still relevant?
Oh,
Or
yeah,
is it
yeah.
out of date? No,
Yeah.
it's still good.
Yeah, completely. Yeah, so
I was
that
reading
will,
through it, but I was like, well, maybe it's 1944, maybe.
yeah, it's perfect. The atomic physics is the same. Okay? But finally, it says, Hund's third rule, all right, this is number C, is that if a subshell is no more than half filled, then the lowest energy level has J equals L minus S. All right? So is this carbon less than half filled?
No.
Yeah, it's 2 out of
Yeah,
6.
it has 2. 2 out of 6, it's less than half filled. All
It
right?
should be,
So J should be L minus S.
which is, in this case, would be 0,
So what should the answer be for this?
3, 0.
The triplet P0. Okay?
See, I don't understand the way he explained number 2 at all, or B.
Okay. Yeah.
Like, he doesn't explain when he uses on top of that. I don't know what that means, it's just a word.
Okay, so top of the ladder means if you looked at the solutions, right?
Yeah, and it didn't make any sense.
And what it does is those are the Clebsch-Gordon
It
coefficients.
was, I thought it looked like Klux-Gordon, and I tried using that, but I was
Yeah.
like, well, maybe it's not.
And so check this out. For the Clebsch-Gordon coefficients, if I'm coupling together two momenta, angular momenta, and I have the highest and the lowest possible angular momenta, right? If I look out and build the highest and the lowest angular momenta you can get out of two angular momenta, that necessarily means that the angular momenta have to be in the same direction. And that necessarily means that they're in a symmetric wave function. Okay? So what he was trying to tell you in the solutions here is that if you went to the top of the ladder in terms of what you could do to couple together angular momenta, what you would do is you would end up seeing that the Clebsch-Gordon coefficients are just, they're not a sum of anything, they're just the two maximum states, and that is necessarily symmetric.
So then you can use the Klux-Gordon to find the next one too? Or?
Well, you know, for this one, it's a little bit messy because on this one, Dale, it just tells you that the maximum one is symmetric. It can't tell you necessarily the others. Okay, so that was just a trick in this case to see the maximum one.
So top of ladder just means look at the maximum angular momentum.
So given two angular momenta that you're coupling together, it is the highest amount of total angular momentum that you can get out of that system. And it necessarily has to be this, which is symmetric. Okay?
For carbon, it could be anti. For another atom, it may not be symmetric, right?
If it's, even if it's another atom, if it's the most angular momentum, so like this, it's the maximum angular momentum for L that you could get out of it.
But if you only had one p orbital, it'd be
Right, then you can't use that argument. You can't use the top of the argument, the top of the ladder argument. Like right even here, it's a little ambiguous. How do I know for sure that that's antisymmetric? Right? Maybe you could get it out of it.
This whole thing about S being symmetric, P being anti, is that something that comes from atomic physics, or?
Yeah, yeah. So I think what all you have to do is you have to look at the spherical harmonics, because the spherical harmonics define the state LML, and if you look at those, they will be symmetric or antisymmetric. Okay? And that's again with respect to so yeah, so I'm not clear how to prove that right away. All right.
It would be in Würzburg.
Yeah. All right, I don't have a clear idea right away. Okay. The next problem I gave is 514, where it talked about this element dysprosium. All right, and it's not at all clear necessarily how to go about filling up those shells, right? You know, it's easy to start off with 1s squared, 2s squared, 2p6, 3s squared, 3p6, 3p10. Everybody should be able to do that, right? And then 4s squared and so on. So generally speaking, you would just, keep going to higher principal quantum numbers and filling up all the shells, all right? But if you look at an atomic physics book, all right, what you can do is look at the energy levels of all these orbitals, and what you'll start to see that as you go up, some of the like as you go up in N and L, you'll start to see other N's with even higher L's having lower energy, all right, than the N you were at. So say N equals 4 and N equals 5. 5 has some L's that are much higher than what N equals 4 has, and the energy of those states will fall below the last L in N equals 4.
And that's because the nucleus is being shielded, right, by what I think what the word is.
Yeah, it has to do with
I think that's.
How does it do with the radius of the electron in the first place?
it has to do with everything. All right, that when you start to fill up the shells, you want to again keep the electrons as far away as possible, and so at some point you can go up in a shell, right, and keep the electrons further away to reduce that electron-electron interaction so that it will be below the others. But certainly I'm not going to hold you to that either, and there was essentially no discussion of this whatsoever.
Yeah, he didn't say which way they go past.
Yes, there's no discussion
I
whatsoever.
mean, he mentioned it, but he didn't say which ones to use, and I did it out just straight and it didn't come out right. And then
Right.
his answer in the solution manual is different than what Herzberg is.
Okay.
And Herzberg says that they're unknown. They're possible,
Okay,
but unknown.
so this is now known,
Oh,
all right?
well, they're
So,
not known. It was unclear or something like that.
okay, so it's more clear now.
Huh.
All right, and the only reason that I even threw that in is because that's one of the atoms that Dave DeMille works on at Yale, dysprosium. So Dave is an expert on that and knows that configuration and knows the energy levels of that very, very well. All right? Okay. All right. So then next up, we started doing Fermi energy, and I wanted to clear up some things on that, all right? So I think I can say it in a much better way now. And I don't think I was at all clear about this last time. Okay, so where are we? We're starting to do many electron atoms, all right? What we found out with the many electron atoms is the total wave function has to be antisymmetric, okay? So we're going to move from, and we got some nice things. So we did atoms. We did 1 electron atoms, like hydrogen moles. And then we just did as many electrons. And what we had to keep in mind is that the psi total had to equal psi space times psi spin, and that had to be antisymmetric. Okay? Everybody cool with that? And this got very complicated, But okay. The next step, the new step that we're taking, and maybe I would have made this much clearer in the book. The new step is now what we're going to do, and Griffiths does say solids, but essentially we're going to go to now, instead of many electrons, we're going to go to many atoms. Okay? In the very first model, was a free electron gas. Okay, now, what I want you to note is, right away, is this is 1 electron model still. All right, we're just talking about 1 electron, free electron gas. All right, we're going to make it many electrons a little bit later, but we're starting out that way. All right, and 2 is we're completely ignoring the potential energy, E potential. And then 3 is not gonna worry about the total wave